A man who never existed changed mathematics forever. The name on medieval manuscripts reads Leonardo Pisano, Leonardo of Pisa, but history remembers him by a nickname given centuries after his death, Fibonacci, son of Bonacci, except his father's name wasn't Bonacci. The nickname is probably a mistake, a medieval clerical error that stuck. We don't even know what he looked like. No portraits survive. No physical descriptions exist in contemporary sources. For a man whose sequence appears in sunflowers and galaxies, in Renaissance art and modern algorithms, we know almost nothing about the person himself. What we do know begins in Pisa, sometime around 1170. The exact date is lost. Medieval birth records were inconsistent at best, and Leonardo's family, while respectable, wasn't important enough to warrant careful documentation. Pisa itself was a different world then, a maritime republic growing wealthy from Mediterranean trade, its famous tower already beginning its slow tilt into the soft ground. Leonardo's father was Guglielmo Bonacci, a merchant and customs official. Not Bonacci, Bonacci. The Fibonacci nickname wouldn't appear until the 1800s, invented by a historian who misread or misunderstood the medieval Latin. By then the error was indelible. Guglielmo worked in trade, which meant he understood numbers in a way most Europeans of his time did not. He dealt with currencies, weights, measures, the practical mathematics of commerce. And sometime in the 1180s, when Leonardo was perhaps 10 or 12 years old, Guglielmo received an appointment that would change his son's life, and eventually the history of mathematics itself. The Republic of Pisa maintained a trading post in Bugia, a port city on the North African coast in what is now Algeria. Bugia was a crossroads, a place where Italian merchants met Arab traders, where goods from across the Mediterranean and beyond changed hands. Guglielmo was sent there as a public official, essentially a combination trade representative and customs inspector. He brought his son with him. Imagine being a boy from Pisa, a city of perhaps 30,000 people, arriving in Bugia. The languages alone would have been overwhelming. Arabic, Berber dialects, Italian, Latin, probably Greek and Hebrew from other merchants. The goods passing through the port came from places Leonardo had only heard about in stories. Spices from India, silk from China, gold from sub-Saharan Africa. But what captured the boy's attention wasn't the exotic cargo, it was how people counted. Europeans in 1180 used Roman numerals for almost everything. You've seen them. I, V, X, L, C, D, M. Try multiplying 24 by 17 in your head. Go ahead, it's painful. Roman numerals work fine for recording quantities or marking chapters in books, but they're terrible for calculation. Merchants kept abacuses nearby because doing arithmetic with Roman numerals required physical computing devices. The Arab merchants in Bugia used something different. They wrote numbers with strange symbols, 1, 2, 3, 4, 5, 6, 7, 8, 9, and they had a symbol for nothing, for zero, zero. These weren't Arab inventions. The system had come from India centuries earlier, but the Arabs had refined it, spread it across their trading networks, developed sophisticated mathematics using it. Leonardo watched Arab clerks multiply large numbers on paper. No abacus needed. They could divide, calculate percentages, solve problems that would take a European merchant hours using Roman numerals. The efficiency was stunning. Somewhere in Bugia, someone taught the Italian boy this system. We don't know who. A clerk in his father's office, a merchant his father befriended, a professional teacher. The historical record is silent. But Leonardo learned not just the symbols, but the algorithms, the methods for using them. Addition, subtraction, multiplication, division. All done with pen and paper. He was hooked. Over the next several years, as Guglielmo conducted his business, Leonardo studied. When Pisan trading ships stopped in Bugia, carrying merchants from other Mediterranean ports, Leonardo questioned them about mathematics. He learned that different regions used variations of the system, that mathematicians in Egypt knew techniques unknown in Syria, that scholars in Sicily were beginning to translate Arabic mathematical texts into Latin. He began to travel, though the details are frustratingly vague. Leonardo himself mentions visiting Egypt, Syria, Greece, Sicily, and Provence. Whether these were extended study trips or brief stops during trading voyages, we don't know. How he funded this travel is unclear. Was he working for his father's business? Had he become a merchant himself? Was someone sponsoring his education? What we do know is that he sought out mathematicians wherever he went. In an era before universities were common, before printed books existed, mathematical knowledge was scattered, held by individual scholars, traders, and officials who needed it for practical work. Leonardo collected this knowledge like other men collected coins. By his late 20s, Leonardo had assembled an understanding of mathematics that almost no one in Western Europe possessed. He knew the Hindu-Arabic number system intimately. He'd studied the works of Muhammad ibn Musa al-Khwarizmi, the Persian mathematician whose name would eventually become the word algorithm. He understood algebraic techniques that wouldn't appear in European universities for another century. And then he went home to Pisa. The Pisa that Leonardo returned to around 1200 was thriving. Maritime trade was expanding. The city was locked in commercial and military competition with Genoa, Venice, and other Italian republics. Money was flowing, merchants were getting wealthy, and all of them were still calculating with Roman numerals and abacuses. Leonardo saw an opportunity. He understood something profound. The Hindu-Arabic number system wasn't just more efficient, it was fundamentally superior. It enabled mathematics that Roman numerals made nearly impossible. And in a city of merchants, anyone who could calculate faster, more accurately, with less effort, would have an enormous advantage. So he decided to write a book. This wasn't an obvious decision. Books in 1200 were rare and expensive, each copy painstakingly written by hand. There was no market for mathematics textbooks because there were almost no students of mathematics. Universities were just beginning to emerge in Europe. The primary readers of advanced texts were clergy and the very few scholars attached to royal courts. But Leonardo wasn't writing for scholars, he was writing for merchants, for the men who dealt in currency exchange, compound interest, profit calculations, partnership agreements, the men who needed practical mathematics every day. He called his book Liber Abachi, the Book of Calculation. The title was modest, the content was revolutionary. The manuscript that Leonardo completed in 1202 ran to hundreds of pages. It opened with an introduction to the Hindu-Arabic numerals, explaining what each symbol meant, how to write them, how they functioned. Then it systematically taught the algorithms for arithmetic: addition, subtraction, multiplication, division, working with fractions. But this wasn't abstract mathematics. Every section was packed with practical examples drawn from real commerce, how to convert between the various currencies circulating in Mediterranean trade, how to calculate the profit on a shipment of goods, how to fairly divide profits among partners who invested different amounts, how to determine whether a money-changing deal was honest or fraudulent. Leonardo was translating the mathematics he'd learned in the Islamic world into a form Italian merchants could use. He wasn't just teaching new number symbols, he was importing an entire mathematical infrastructure. The book circulated in manuscript form. We don't know how many copies were made in Leonardo's lifetime, but it found its audience. Merchants discovered they could perform calculations in minutes that previously took hours. The competitive advantage was real and immediate, and buried in this practical manual, in a section discussing a problem about breeding rabbits, was the sequence that would make Leonardo famous 8 centuries later. The problem seems simple, almost silly. Suppose you have a pair of rabbits, one male and one female. Each month, every mature pair produces a new pair. Baby rabbits take 1 month to mature. How many pairs will you have after a year? The answer creates a pattern. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. Each number is the sum of the previous two. Start with 1 and 1. Add them to get 2. Add the last two numbers to get 3, then 5, then 8. The sequence continues infinitely. Leonardo probably didn't invent this sequence. Similar patterns appear in earlier Sanskrit texts on poetry meter, but he introduced it to European mathematics, and he recognized something interesting about it. Though he couldn't have known how interesting, this sequence shows up everywhere in nature. The spirals of a nautilus shell follow it. The arrangement of sunflower seeds follows it. Pine cones, pineapples, the branching of trees, the breeding patterns of bees, all contain this pattern. The ratio between consecutive numbers in the sequence approaches the golden ratio, a proportion that appears in art and architecture across cultures. But in 1202 it was just a clever problem about rabbits, tucked into a book about mercantile mathematics. Leonardo didn't stop with Liber Abachi. Over the next 3 decades he wrote several more mathematical works, each exploring different aspects of the knowledge he'd gathered. Practica Geometria, the practice of geometry, applied similar practical approaches to geometric problems. Flos, the flower, discussed solutions to cubic equations. Liber Quadratorum, the Book of Squares, explored number theory. These later works were more theoretical, less focused on immediate commercial application. Leonardo was pushing into pure mathematics, exploring problems for their own sake. He was particularly interested in Diophantine equations, problems involving finding integer solutions to algebraic equations. Some of his work wouldn't be surpassed for centuries. But who was reading these advanced treatises? The audience was tiny. A handful of scholars, perhaps some teachers at the emerging universities, maybe a few unusually educated merchants or nobles. Medieval Europe simply didn't have a large community of mathematicians. Leonardo's reputation grew within this small world. He came to the attention of the Holy Roman Emperor Frederick II, one of the most remarkable rulers of the Middle Ages. Frederick was unusual for his time. He spoke 6 languages, corresponded with Islamic scholars, maintained a diverse court of Christians, Muslims, and Jews, and had a genuine interest in science and mathematics. Around 1225, when Frederick was holding court in Pisa, he arranged a mathematical competition. Leonardo was invited to participate, essentially a medieval math tournament where scholars would solve problems posed by the emperor's court mathematicians. One problem involved finding a number that, when you add or subtract certain values and then square the result, produces perfect squares. It's a type of Diophantine equation, exactly the kind of number theory Leonardo had been studying. He solved it, though we don't have the details of the competition itself. Frederick was impressed enough to grant Leonardo a salary, essentially making him a court mathematician. This was recognition of the highest order, acknowledgement that this merchant's son from Pisa was doing mathematics at a level worthy of imperial patronage. And then Leonardo vanished from history. We know he was alive in 1228 because the Republic of Pisa granted him a salary in recognition of his service, advising the city on accounting matters. After that, nothing. No death date, no records. The man who revolutionized European mathematics simply disappears from the documentary record. He probably died sometime in the 1240s, but we don't know where, when, or how. There's no tomb, no memorial, no contemporary obituary. For a man who changed how an entire civilization calculated, the ending is frustratingly obscure, but the silence tells us something important. Leonardo wasn't famous in his own time, not in the way we think of fame. He was respected within the tiny world of medieval mathematics known to merchants who used his methods, recognised by Frederick's court. But he wasn't a household name. Mathematics itself wasn't considered particularly important outside its practical applications. The real impact of his work would unfold over centuries, as the Hindu-Arabic number system he championed gradually displaced Roman numerals across Europe. As merchants discovered that yes, these new numbers really did make commerce easier. As scholars realised that whole branches of mathematics became possible once you could write and manipulate numbers efficiently. By the time Leonardo died, probably in the 1240s, he'd planted seeds that wouldn't fully sprout for generations. The Hindu-Arabic numerals were spreading, but slowly. Rome hadn't been built in a day, and it wouldn't be demolished overnight either. The Roman numeral system had inertia, centuries of habit, countless documents written in the old notation, scribes trained in traditional methods. You don't just flip a switch and change how an entire civilization counts. But the momentum was building. Each merchant who adopted the new system became a walking advertisement for its superiority. Each clerk who learned to calculate with Hindu-Arabic numerals discovered he could work faster and with fewer errors. The advantages were simply too obvious to ignore forever. Universities played a crucial role in the transition. As these institutions emerged and grew throughout the 13th century, they needed standardized methods for teaching mathematics. The abacus schools of Italy, where young merchants learned arithmetic, increasingly incorporated the new numerals into their curriculum. Leonardo's Liber Abachi became a foundational text, copied and recopied, passed from teacher to student. The printing press, still 2 centuries away, would eventually make the victory of Hindu-Arabic numerals inevitable. But even before Gutenberg, the system was winning through sheer utility. By 1300, most Italian merchants kept their books using the new numbers. By 1400, the practice had spread across much of Europe. By 1500, Roman numerals were being relegated to specific ceremonial uses: clock faces, building inscriptions, regnal numbers for kings and popes. Think about what this meant in practical terms. A merchant in 1150 doing multiplication had to be a kind of specialist, someone trained in complex techniques or reliant on counting boards. A merchant in 1350 could do the same calculation with pen and paper in a fraction of the time. This wasn't a minor improvement, it was the difference between mathematics being an arcane art practiced by specialists and a tool accessible to anyone willing to learn. The ripple effects went far beyond commerce. Science became possible in new ways. You can't do sophisticated astronomy or physics when your number system makes calculation a nightmare. Copernicus, Galileo, Newton, their work depended on being able to manipulate numbers efficiently. The scientific revolution of the 16th and 17th centuries rested on mathematical foundations that Hindu-Arabic numerals made practical. Engineering advanced, architecture became more ambitious, accounting grew more sophisticated, banking developed complex instruments, insurance became mathematically rigorous. Every field that required numerical precision benefited from the revolution Leonardo helped catalyze. But here's what's strange. Leonardo himself was largely forgotten. His books circulated, yes, but often without attribution. His name wasn't attached to the Fibonacci sequence during his lifetime. That connection wouldn't be made until centuries later, when 19th century mathematicians studying the history of their field rediscovered his work and started calling him Fibonacci, a name he never used himself. The sequence that bears his name appeared in Liber Abachi as a solution to a thought experiment about rabbit breeding. It's the kind of recreational mathematics that has always fascinated people. Assume you start with one pair of rabbits, and every month each pair produces a new pair, which becomes reproductive after 1 month. How many pairs do you have after a year? The answer produces a sequence: 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. Each number is the sum of the two preceding numbers. Leonardo presented this as a curiosity, an interesting pattern. He had no idea that this sequence would show up everywhere in nature and mathematics. The arrangement of leaves on a stem, the spirals in a sunflower, the proportions of a nautilus shell, the breeding patterns of bees, all follow Fibonacci numbers. The golden ratio, approximately 1.618, which artists and architects have considered the most aesthetically pleasing proportion, is intimately related to the Fibonacci sequence. As you go further in the sequence, the ratio between consecutive numbers approaches the golden ratio with increasing precision. Leonardo didn't discover this connection. He just noticed an interesting pattern in rabbit reproduction. This is how mathematics often works. Someone explores a problem for one reason, and centuries later, we discover their solution illuminates something completely different. Leonardo was interested in practical arithmetic for merchants. His recreational rabbit problem turned out to describe fundamental patterns in nature. He had no way of knowing. The rediscovery of Leonardo's work in the 19th century was part of a broader historical project. Mathematicians and historians were tracing the development of their discipline, following the threads backward through time. They found Leonardo's books in libraries and archives, recognized their importance, and started calling him Fibonacci. The name stuck. Today, if you mention Leonardo of Pisa to most people, you'll get blank stares. Say Fibonacci, and anyone who studied mathematics will know exactly who you mean. He's become famous for something he barely emphasized in his own work. Known by a name he never used, celebrated for contributions he couldn't have imagined. There's a statue of him in Pisa now, erected in the 19th century. It stands in a cemetery, the Camposanto Monumentale, overlooking the city. The inscription celebrates his introduction of Hindu-Arabic numerals to Europe. The statue depicts him holding a scroll, the embodiment of learning and mathematical wisdom. It's a nice gesture, but it comes about 6 centuries too late to mean anything to the man himself. What would Leonardo think if he could see the modern world? A world where his number system is so universal we don't even think about it anymore. Where children learn to count using Hindu-Arabic numerals as naturally as they learn to speak. Where computers process billions of calculations per second using the binary descendants of the decimal system he championed. He'd probably be most surprised by the Fibonacci sequence becoming famous. Of all the mathematics in his books, the rabbit problem was a throwaway, a bit of recreational number theory to amuse readers. The serious work, the algebra, the methods for solving cubic equations, the techniques for commercial calculation, that was what mattered to him. But history has its own priorities. The broader transformation Leonardo embodied, the transmission of knowledge between civilizations, is worth considering. The Hindu-Arabic numerals weren't European. They came from India, were refined in the Islamic world, and arrived in Christian Europe through the work of translators and travelers. Leonardo was a conduit, a bridge between intellectual traditions that were often hostile to each other. Medieval Europe and the Islamic world were frequently at war. The Crusades raged throughout Leonardo's lifetime. Religious tensions ran high, trade happened, but suspicion and conflict were constant. Yet mathematical knowledge flowed across these boundaries. Scholars on both sides recognized that truth transcends politics. The House of Wisdom in Baghdad, where Islamic mathematicians had built on Greek and Indian foundations, represented an intellectual tradition Europe desperately needed. Leonardo brought back not just numbers but an attitude toward mathematics, rigorous, systematic, willing to learn from foreign sources. This cosmopolitan approach to knowledge would eventually become one of Europe's strengths, but the transmission was selective. Europe adopted the mathematics while remaining deeply suspicious of Islamic culture generally. The numbers were useful, so they spread. Other aspects of Islamic learning took longer to penetrate European consciousness, if they ever did. Knowledge transfer is always complicated, always filtered through existing prejudices and priorities. Leonardo himself seems to have been pragmatic about these issues. He learned from Arabic sources without apparent anxiety about their origins. He presented Hindu-Arabic numerals as superior to Roman numerals based on their utility, not their cultural pedigree. This was radical in an era when European intellectuals often dismissed non-Christian learning as inherently suspect. The merchant culture that produced Leonardo had its own kind of cosmopolitanism. Trade required dealing with people from everywhere. Merchants couldn't afford to be too picky about where good ideas came from. If a mathematical technique made accounting easier, you used it, regardless of whether it originated in India, Arabia, or Greece. This practical attitude helped European commerce advance faster than European theology. By the 14th century, a new class was emerging in European cities: educated merchants who could read, write, calculate, and navigate the increasingly complex world of international trade. They weren't nobles, weren't clergy, but they had money, literacy, and mathematical competence. The rise of this bourgeoisie would eventually transform European society, helping to create the conditions for the Renaissance, the Reformation, and eventually the modern world. Leonardo stood at the beginning of this transformation. The tools he provided, Hindu-Arabic numerals, systematic arithmetic, algebraic techniques, gave merchants the mathematical foundation they needed to operate at scale. Banking, insurance, joint stock companies, double-entry bookkeeping, all of these innovations depended on the kind of numerical precision that Leonardo's system made possible. Consider double-entry bookkeeping, developed in Italy in the decades after Leonardo's death. This accounting method, where every transaction is recorded twice to maintain balance, requires extensive calculation. Try doing it in Roman numerals. It's possible technically, but so cumbersome that you'd probably give up. With Hindu-Arabic numerals, it's straightforward. The Medici Bank, the Fuggers, the great commercial enterprises of the Renaissance, they all depended on accounting methods that presupposed efficient arithmetic. Or consider the development of perspective in Renaissance art. Brunelleschi's demonstration of linear perspective in the early 15th century required mathematical calculation. Artists needed to determine vanishing points, calculate proportional diminution, work out the geometry of three-dimensional space projected onto a two-dimensional surface. This wasn't impossible with Roman numerals, but it was far easier with the tools Leonardo had introduced 3 centuries earlier. The mathematical revolution Leonardo participated in was quiet, almost invisible. There were no dramatic battles, no sudden revelations, no eureka moments that changed everything overnight. Just the slow accumulation of practical advantages as more people realized that yes, this new way of writing numbers really did make life easier. Resistance persisted for centuries. Some churches continued using Roman numerals in their records long after merchants had switched. Legal documents maintained traditional notation because scribes feared that the new numbers could be too easily altered or forged. 4 could become 9 with a single stroke after all. Roman numerals, with their distinct letter forms, seemed more secure. These concerns weren't entirely unfounded. The transition to Hindu-Arabic numerals did create new opportunities for fraud. But the advantages outweighed the risks, and eventually even the most conservative institutions made the switch. The last holdouts were ceremonial uses, cornerstones, monuments, regnal years, places where numbers served symbolic rather than computational purposes. By the time of Leonardo's death, the outcome was probably inevitable, though nobody could have known it yet. The system he'd championed was simply too useful to be stopped. The advantages were too clear, the applications too numerous. Europe would calculate with Hindu-Arabic numerals, and the entire trajectory of Western science and commerce would be shaped by that choice. And yet the man who did more than anyone to make this happen died in obscurity, his final years unrecorded, his burial place unknown. History is full of such ironies. The people who change everything often don't live to see the results. The seeds they plant grow into forests, but the gardener is long gone. Leonardo's final years remain shadowy. We know he was still in Pisa in the 1240s because a city decree from that period mentions him by name, granting him a salary as a municipal consultant. The Republic of Pisa was paying him to advise on matters of accounting and calculation, a recognition of his expertise. But beyond this official record, we have almost nothing. Did he continue writing? Did he teach students privately? Did he maintain correspondence with other scholars? We don't know. The documentary trail goes cold. Some historians believe he died around 1250. Others push the date later. His death wasn't recorded in any surviving document. For a man whose work would reshape European mathematics, the silence surrounding his final decade is startling. No contemporary wrote an obituary. No student penned a memorial. He simply faded from the record, as countless medieval figures did, leaving behind his books and the consequences of his books, but little else. What we can trace is the spread of his ideas across the next 2 centuries. The Liber Abachi didn't become an instant bestseller. Books didn't work that way in the medieval world. Each copy had to be laboriously handwritten. A complete manuscript of the Liber Abachi required hundreds of hours of scribal labour, making it expensive and rare. But the manuscripts that did exist began to circulate among merchants, mathematicians and teachers. They were copied, sometimes in full, sometimes in abridged versions, sometimes with additional material added by later scholars. One of the most important early followers was Maestro Benedetto, a Florentine mathematician who wrote a treatise on arithmetic and geometry around 1290. His work drew heavily on Leonardo's, though he rarely mentioned his source by name. This was standard medieval practice. The concept of intellectual property, as we understand it, didn't exist. If you found useful material in another scholar's work, you incorporated it into your own, without necessarily providing attribution. Another key figure was Paolo dell'Abaco, who taught commercial mathematics in Florence in the early 14th century. His textbooks, designed for the sons of merchants, were essentially adaptations of Leonardo's methods stripped down to practical essentials. Less theory, more worked examples. Less mathematical beauty, more immediate utility. These teaching texts, called Abaco books, after the calculation schools where they were used, proliferated across Italian cities. Florence, Venice, Genoa, Milan, each developed its own tradition of commercial mathematics education, all descended from Leonardo's work. The Abaco schools were private institutions, often run by a single master who taught boys the mathematics they'd need in trade. Reading, writing, basic Latin, but most importantly, arithmetic and practical geometry. The curriculum was intensely practical. How to calculate exchange rates between currencies, how to determine profit margins, how to measure cloth, wine, grain, how to calculate interest on loans, how to divide partnerships fairly when merchants pooled resources. Every problem was drawn from the actual business world these boys would enter, and the notation was always Hindu-Arabic. Roman numerals appeared in the Abaco books only when quoting legal documents or explaining how to convert old records. The future belonged to the new system, and the Abaco masters knew it. The Abaco tradition produced something remarkable: widespread mathematical literacy among a non-aristocratic, non-clerical class. By the early 15th century, Florence alone had 6 Abaco schools serving hundreds of students. Venice had more. These boys weren't being trained as scholars or philosophers. They were being trained as merchants, but they were learning real mathematics, and some of them learned to love it. One such student was Luca Pacioli. Born in 1447 in the small town of San Sepolcro, Pacioli studied at an Abaco school, showed exceptional talent, and eventually became a Franciscan friar and mathematician. In 1494, he published the Summa di Arithmetica, a massive encyclopedia of mathematical knowledge that became one of the first printed mathematics books. Pacioli's Summa drew extensively on Leonardo's work, particularly the Liber Abachi, but by 1494, printing had transformed the landscape of knowledge. What had once required months of scribal labour could now be reproduced in weeks. Pacioli's book reached readers across Europe. It was dense, difficult, comprehensive, and hugely influential. Among its readers was a young German artist named Albrecht Dürer, who used Pacioli's geometric sections to understand perspective and proportion. Also among its readers was a young Italian engineer named Leonardo da Vinci, who collaborated with Pacioli on problems of geometry and became fascinated by mathematical form. The chain of influence runs directly from Leonardo Fibonacci through the Abaco tradition, through Pacioli to the giants of the Renaissance. Without claiming too much, without falling into the trap of making one man responsible for everything that came after, we can see the connection. The tools Leonardo introduced made certain kinds of thinking easier, and that ease enabled developments that might otherwise have been delayed or might never have happened at all. Consider the calendar. The Julian calendar, established by Julius Caesar in 45 BCE, was based on a year of 365.25 days. Close, but not quite right. The actual solar year is about 11 minutes shorter. Those 11 minutes add up. By the 16th century, the calendar had drifted by 10 days. The spring equinox, which was supposed to fall around March 21st, was occurring on March 11th. This was a problem for the Church, which calculated Easter based on the spring equinox. Pope Gregory XIII commissioned a reform. The result was the Gregorian calendar, introduced in 1582, which corrected the drift by skipping 10 days that October and adjusting the leap year rules. The calculations required were complex. Astronomers and mathematicians had to determine the precise length of the solar year, calculate the accumulated error, design a new leap year system that would prevent future drift, and convince a skeptical world to accept the changes. Try doing any of this efficiently with Roman numerals. The Gregorian reform depended on the kind of precise astronomical calculation that the Hindu-Arabic system made possible. The scholars who designed it, Aloysius Lilius, Christopher Clavius, and others, used the numerical tools that Leonardo had helped introduce to Europe 3.5 centuries earlier. Or consider navigation. The age of exploration began in the 15th century, Portuguese sailors inching down the African coast, Spanish expeditions crossing the Atlantic, eventually Magellan's circumnavigation of the globe. These voyages required sophisticated mathematics, calculating latitude from the height of the sun, dead reckoning across thousands of miles of open ocean, determining longitude, one of the hardest problems in early modern science. Navigators used tables of trigonometric functions, astronomical almanacs, complex instruments like the astrolabe and the cross staff. The calculations involved were constant and demanding. Roman numerals would have made this work nearly impossible. Hindu-Arabic numerals made it merely very difficult. The expansion of European power across the globe depended on many factors: ship design, military technology, disease, political organization. But it also depended on the ability to calculate where you were and where you were going. The mathematics of navigation was built on the foundation Leonardo had helped establish. The scientific revolution of the 17th century is the most obvious beneficiary. Galileo's careful measurements of falling bodies, Kepler's calculations of planetary orbits, Newton's universal law of gravitation, all of this required extensive numerical work. The Hindu-Arabic system wasn't sufficient to produce modern science, but it was necessary. You cannot build physics without the tools to calculate. Kepler, working out the orbit of Mars in the early 1600s, performed calculations that filled hundreds of pages. He tested hypothesis after hypothesis, each requiring extensive arithmetic. When he finally discovered that planets move in ellipses, not circles, the proof required showing that his elliptical model matched Tycho Brahe's observations better than any competing theory. This meant calculation upon calculation upon calculation. With Roman numerals, Kepler's work would have taken decades instead of years, or more likely, it wouldn't have happened at all. The sheer tedium would have defeated him. Newton's Principia Mathematica, published in 1687, is written in geometric language rather than the algebraic notation we'd use today. But the calculations behind it, the working out of planetary motions and gravitational forces, required arithmetic. Newton used Hindu-Arabic numerals for his calculations, even if he presented his results in classical geometric form. The entire edifice of modern science rests on measurement and calculation. The story of how Europe acquired the mathematical tools to build that edifice is a story Leonardo Fibonacci helped write, even though he died 3 centuries before the scientific revolution began. There's a tendency in history to look for single turning points, decisive moments when everything changed. The invention of the printing press, the Protestant Reformation, the French Revolution. These are real and important, but they're also somewhat misleading. Most change is gradual, the accumulation of small shifts that eventually produce a transformed landscape. The adoption of Hindu-Arabic numerals was this kind of change. Slow, incremental, almost invisible to the people living through it. Leonardo wrote his books. Some merchants started using the new methods. More merchants followed. Teachers began including Hindu-Arabic arithmetic in their curricula. Scholars adopted the notation for specialized work. Eventually it became standard, then universal, then so thoroughly naturalized that people forgot it had ever been controversial. By 1600, educated Europeans wrote numbers the way we do. They'd been doing it for so long that many had probably forgotten any other way existed. Roman numerals survived in ceremonial contexts, on monuments and cornerstones. But for actual calculation, they'd been abandoned. The transformation was complete, and Leonardo's role in it had been largely forgotten. His name survived in mathematical circles. Scholars knew about the Liber Abachi, though few had actually read it. But the general educated public had no idea who he was. He'd become a footnote, a specialist's reference, a name in the genealogy of mathematics that most people never learned. And then, in the 19th century, something unexpected happened. Mathematicians rediscovered a sequence hidden in the Liber Abachi, tucked away in a problem about breeding rabbits. The sequence was elegant, mysterious, and seemed to appear everywhere in nature. Suddenly Leonardo Fibonacci was famous again, 7 centuries after his death, for something he'd probably considered a minor curiosity. The rabbit problem appears in the 3rd section of the Liber Abachi. Leonardo poses it as a recreational problem, the kind of puzzle designed to demonstrate mathematical reasoning rather than solve a practical question. Here's how it goes. A man puts a pair of rabbits in an enclosed space. Assume rabbits begin breeding at 1 month old. Each month, every mature pair produces a new pair. How many pairs will there be after a year? Month 1, 1 pair. Month 2, still 1 pair since they're not yet mature. Month 3, 2 pairs, the original plus their first offspring. Month 4, 3 pairs. Month 5, 5 pairs. Month 6, 8 pairs. The sequence continues. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. Each number is the sum of the previous 2. This pattern, now called the Fibonacci sequence, has properties that fascinated mathematicians for centuries after its rediscovery. Leonardo himself didn't dwell on it. He included the rabbit problem as one example among hundreds, showed the solution, and moved on. He had no special name for the sequence. He didn't investigate its properties or recognize its broader significance. It was just another problem. But in the 19th century, mathematicians began noticing something strange. The ratio between consecutive Fibonacci numbers approaches a specific value as the sequence continues. 8 divided by 5 is 1.6. 13 divided by 8 is 1.625. 21 divided by 13 is approximately 1.615. The ratio oscillates but converges toward 1.618, a number known as the golden ratio, or phi. This number had been known since ancient Greece. Euclid described it. Classical architects used it, but nobody had connected it to the rabbit sequence until the 1800s. And once that connection was made, people started finding Fibonacci numbers everywhere. The spiral arrangement of seeds in a sunflower head follows Fibonacci numbers. The branching pattern of trees approximates the sequence. Pineapple scales, pine cones, nautilus shells all show Fibonacci patterns. Whether this represents deep mathematical truth about biological growth or simply human pattern seeking is still debated, but the observations are real. Human interest in the sequence exploded. Artists claimed the golden ratio produced ideal proportions. Architects incorporated it into building designs. Mystics found profound significance in its ubiquity. The Fibonacci sequence became part of popular culture, appearing in novels, films, and conspiracy theories. And suddenly, 600 years after his death, Leonardo Fibonacci was famous. The irony couldn't be sharper. During his lifetime, Leonardo worked to make Hindu-Arabic numerals accessible to merchants who needed practical tools for commerce. He wrote detailed explanations of multiplication and division, currency conversion, and compound interest. He showed traders how to calculate profit margins and split partnerships fairly. His book was a manual for business mathematics, grounded in the real world of buying and selling. And what made him immortal? A whimsical puzzle about rabbits that he probably spent an afternoon composing. The sequence bears his name now, though he never called it that. The term Fibonacci sequence wasn't coined until the 19th century, when French mathematician Édouard Lucas was studying number theory. Lucas attached Leonardo's nickname to the pattern, and the name stuck. It's fitting in a way. Leonardo Pisano, the serious mathematician, faded from memory, but Fibonacci, the name that emphasized his illegitimate birth, became eternal. What would Leonardo have thought about this? We can only speculate. He might have been pleased that mathematics he'd introduced was still studied centuries later, or he might have been frustrated that a minor recreational problem overshadowed what he considered his serious work. The Liber Abachi contains groundbreaking explanations of algebraic methods. It presents solutions to complex problems that wouldn't be systematically addressed in Europe for another 3 centuries. And yet most people who recognize the name Fibonacci couldn't tell you anything else he accomplished. The 19th century rediscovery changed how historians viewed medieval mathematics. Scholars began examining the Liber Abachi more carefully, recognizing its sophistication. They traced Leonardo's influence through the manuscripts that had survived. They documented how his notation spread, how his methods were adopted, how European calculation slowly transformed. But even among specialists, Leonardo's reputation remained complicated. He wasn't quite a mathematician in the modern sense. He didn't prove theorems or develop abstract theories. He was more like an exceptionally talented technical writer who understood mathematics deeply and could explain it clearly. His genius was pedagogical and practical rather than theoretical. This makes him difficult to categorize. History prefers clear narratives. We want Leonardo to be either a revolutionary genius or a mere transmitter of others' knowledge. The reality is messier. He was both and neither. He brought Eastern mathematics to Europe, but he also transformed it in the translation. He solved practical problems, but the methods he used were profoundly sophisticated. He wrote for merchants, but he advanced the field. Consider what he accomplished with the tools he had. No printing press meant every copy was handwritten. No standardized notation meant he had to invent ways to express operations. No academic infrastructure meant he worked essentially alone. No wealthy patron meant he supported himself through practical calculation while pursuing mathematics on the side. And yet he produced a work that remained relevant for 300 years. The Liber Abachi's influence extended beyond mathematics. It changed how Europeans thought about numbers themselves. Before Leonardo, numbers were primarily tools for counting discrete objects. After him, numbers became objects of study in their own right. You could manipulate them, transform them, discover relationships between them. This shift was subtle but profound. It also changed commercial practice in ways Leonardo might not have anticipated. As Hindu-Arabic numerals spread through Italy's merchant houses, double-entry bookkeeping developed. Luca Pacioli would systematize it in 1494, but the numerical foundation was Leonardo's. You can't have modern accounting without place-value notation. The economic transformation of Renaissance Italy depended partly on being able to track complex financial transactions accurately. Leonardo's book made that possible. Banking evolved similarly. The Medici family's financial empire, which would dominate to 15th century Florence, relied on calculation methods that Leonardo had introduced. Interest calculations, exchange rates, loan amortization, all became manageable with Hindu-Arabic arithmetic. The mathematical infrastructure of early capitalism was built on techniques from the Liber Abachi, yet Leonardo himself never accumulated significant wealth from any of this. He was a calculator for hire, not a banker or merchant. He solved problems for others, but apparently never leveraged his expertise into a fortune. Perhaps he lacked business ambition. Perhaps he simply preferred mathematics to money. The historical record doesn't tell us. What we do know is that by the late 13th century, Leonardo's active career had effectively ended. The last dated problem we can attribute to him appears around 1240. After that, silence. He would have been in his 60s, old by medieval standards. Perhaps illness or age forced him to retire. Perhaps he simply decided he'd said everything he wanted to say about mathematics. The circumstances of his death are unknown. No record survives of when or where he died. No contemporary wrote an obituary or memorial. He apparently left no family to preserve his memory. For a man who'd corresponded with Emperor Frederick II, who'd been honoured by the Republic of Pisa, who'd written one of the most important books of his century, the ending was remarkably obscure. This obscurity extended for generations. While merchants used his methods, they rarely knew his name. While scholars copied his manuscripts, they seldom studied his biography. Leonardo became a ghost haunting European mathematics. His presence felt everywhere, but his person forgotten. The Renaissance changed nothing. The printing revolution made books accessible, but the Liber Abachi wasn't printed until 1857. By then, its methods were so standard that nobody needed the original text. The book had succeeded so completely that it made itself obsolete. Even the Fibonacci sequence's fame didn't immediately resurrect Leonardo's broader reputation. People fascinated by the golden ratio and spiral patterns didn't necessarily investigate the medieval mathematician who'd first recorded the pattern. He remained a name attached to a sequence, not a fully realized historical figure. The serious scholarly recovery began only in the 20th century. Historians of mathematics started examining medieval sources more carefully. They traced the transmission of knowledge from Islamic world to Christian Europe. They documented the slow emergence of modern mathematical notation, and they recognized that Leonardo of Pisa stood at a crucial juncture in this history. Modern biographers have attempted to reconstruct his life from fragments. They've analysed the Liber Abachi's structure for autobiographical clues. They've searched Pisan archives for mentions of the Fibonacci family. They've tried to identify which North African cities Leonardo visited, but the evidence remains thin. We know what he wrote far better than we know who he was. This creates a strange situation. The Fibonacci sequence is taught to schoolchildren worldwide. Millions of people can recite the beginning. 1, 1, 2, 3, 5, 8, 13. But ask those same people who Fibonacci was, and most will struggle. An Italian mathematician? Medieval? That's about as specific as it gets. Does this matter? In one sense, no. The mathematics exists independent of its creator. The sequence would work the same way whether we called it the Fibonacci sequence or something else entirely. Knowledge transcends the individuals who discover it. But in another sense, it matters profoundly. Leonardo's story illustrates how knowledge actually spreads, not through lone geniuses working in isolation, but through networks of exchange and translation. Not through sudden revelations, but through patient compilation and explanation. Not through revolutionary breakthroughs, but through making existing knowledge accessible. The Hindu-Arabic numeral system wasn't invented in Europe. Leonardo didn't create it, but he made it European. He took a foreign system and showed his countrymen why it mattered. He translated not just the symbols, but the mathematical thinking behind them. This kind of work is less celebrated than original discovery, but it's equally necessary. Every scientific revolution depends on people like Leonardo. Someone has to bridge cultures, translate concepts, explain patiently to skeptical audiences why new methods are better than old ones. Someone has to write the textbooks that the next generation will learn from. Someone has to be the hinge between what was and what will be. Leonardo fulfilled this role perfectly, which is probably why he was forgotten. Textbook writers rarely become famous. Translators work in obscurity. The people who make knowledge accessible are overshadowed by those who generate it. We remember Newton and Leibniz, who invented calculus. We forget the hundreds of teachers who explained calculus to students who then did their own important work. But occasionally, through historical accident, the translator gets rediscovered. The sequence brings people to Leonardo. They learn about the Liber Abachi. They realize that modern arithmetic, the foundation of all subsequent mathematics, had to be introduced to Europe somehow. And they find this merchant son from Pisa who spent his life calculating and explaining. The fascination with Fibonacci numbers in nature has even sparked new mathematical research. Scientists have investigated why these patterns appear so frequently. Mathematicians have explored the sequence's deeper properties. Computer scientists have found applications in algorithms and data structures. The rabbit problem has generated entire fields of study. None of this would have surprised Leonardo. He knew the sequence was interesting, which is why he included it. He just didn't know it would be the thing he'd be remembered for. Then again, nobody knows which of their works will outlast them. We make our contributions, and history decides what matters. What's certain is that Leonardo changed mathematics in Europe forever. Whether through the slow spread of Hindu-Arabic numerals or the sudden fame of a number sequence, his influence persists. Walk into any classroom where arithmetic is taught, and you're seeing the legacy of a medieval calculator who thought carefully about how to explain numbers to people who'd never seen them before. The story of Leonardo Fibonacci is ultimately about transmission. How knowledge moves between cultures, how new systems replace old ones, how one person's careful work can reshape civilization without anyone noticing it happening. The Hindu-Arabic numerals didn't conquer Europe through force or decree. They spread because they worked better and because someone took the time to explain them properly. That someone was a merchant's son who travelled widely, learned deeply, and written clearly. He wasn't trying to start a revolution. He was trying to help merchants calculate more efficiently. But in doing so, he gave Europe the mathematical foundation it would need for everything that followed. The scientific revolution, the industrial revolution, the digital age. None of it would have been possible without the ability to calculate quickly and accurately. Leonardo probably wouldn't understand a computer or a spaceship, but he'd recognize the numbers that made them possible. Those are his numbers now, the ones he brought home from Bejaia, the ones he spent his life explaining, the ones that, 800 years later, we still use every single day. His monument isn't marble or bronze, it's written in every price tag, every bank statement, every scientific paper. It's in the numbers themselves, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the revolutionary 0. Simple symbols that changed everything. And somewhere in there, hidden in a problem about rabbits, is a sequence that bears his name. Not the name he was born with or the name he used, but the nickname that meant son of nobody much. Fibonacci, the sequence that made him immortal. The sequence appears in unexpected places. Sunflowers spiral their seeds according to Fibonacci numbers. Pine cones arrange their scales in Fibonacci patterns. Pineapples, artichokes, cauliflower, the list goes on. But here's what's strange. Leonardo had nothing to do with discovering this. He never looked at a sunflower and counted spirals. He never examined pine cones for mathematical patterns. He wrote a problem about rabbits, moved on to other calculations, and that was it. The connection between the sequence and nature was discovered much later, centuries later, by botanists and mathematicians who had no idea they were confirming something a medieval Italian had stumbled across while thinking about breeding pairs. This raises a question that doesn't get asked enough. Why does a sequence generated by a completely artificial problem show up in living things? Rabbits don't actually breed according to Fibonacci's rules. The problem was never meant to model reality. It was a mathematical exercise, a puzzle to demonstrate how sequences work, and yet nature uses the same pattern. The answer lies in efficiency. When a plant needs to pack seeds or arrange leaves, it faces a geometric problem. How do you fit the maximum number of items in the minimum space while ensuring each item gets adequate exposure to sunlight and air? The math works itself out. Natural selection favors arrangements that work, and Fibonacci spirals happen to be incredibly efficient. The golden ratio that emerges from the sequence creates optimal packing, not because nature read the Liber Abachi, but because physics and geometry operate by consistent rules. Leonardo would have appreciated this. His entire career was built on recognizing that math describes reality. When merchants needed to calculate profits, when builders needed to measure materials, when anyone needed to solve a practical problem, math provided answers. The fact that his rabbit sequence also describes plant growth would have seemed perfectly natural to him. Math isn't invented, it's discovered. But there's another layer to this story. The Fibonacci sequence isn't actually the Fibonacci sequence. Not originally. Indian mathematicians had already described these numbers centuries before Leonardo was born. Pingala, writing around 200 BCE, explored these patterns in Sanskrit poetry. Virahanka studied them in the 7th century. Gopala and Hemachandra continued the work in the 11th and 12th centuries. They weren't thinking about rabbits, they were analysing poetry. Sanskrit verse has strict metrical rules, and mathematicians wanted to know how many different rhythmic patterns were possible with syllables of different lengths. The calculations led them to the same sequence Leonardo would later rediscover. Same numbers, different context, 600 years earlier. So why is it called the Fibonacci sequence? Because Europe forgot about Indian mathematics. Because transmission of knowledge is messy and incomplete. Because when French mathematician Édouard Lucas popularized the sequence in the 1870s, he didn't know about Pingala or Hemachandra. He knew about Leonardo's rabbit problem, and he gave the sequence a name that stuck. This is how history works. Not fairly, not accurately, but through the accidents of what gets remembered and what gets lost. The Indian mathematicians who first studied these numbers are forgotten by everyone, except specialists. Leonardo, who merely rediscovered them, gets the credit. And the real work that made Leonardo famous, introducing Hindu-Arabic numerals, is overshadowed by the one thing he barely cared about. Recognition follows strange rules. Consider what happened after the Liber Abachi appeared. For decades, almost nothing. A few merchants used the new methods. A few scholars read the book. But most of Europe continued with Roman numerals, because that's what they knew. Change comes slowly, especially when it requires learning an entirely new system. Then something shifted. Universities started teaching the new arithmetic. Merchant schools opened specifically to train young traders in calculation. Books appeared explaining Hindu-Arabic numerals in Italian, German, French. By the early 14th century, 50 years after Leonardo's death, the tide had turned. The old methods were dying. The new ones were spreading. But nobody credited Leonardo. They called it algorithm, after Al-Khwarizmi, the Persian mathematician, whose work Leonardo had studied. They called the numbers Arabic, acknowledging their immediate source. Leonardo's name appeared in some manuscripts, but he wasn't famous. He was just another link in a chain of transmission. The sequence that would eventually make him famous, still buried in the Liber Abachi, noticed by almost no one. The rabbit problem was quirky and interesting, but it wasn't useful. Merchants didn't need to calculate breeding patterns. The real value was in multiplication, division, fractions, practical arithmetic that saved time and money. Centuries passed. The Renaissance came and went. The scientific revolution transformed European thought. Calculus was invented. Modern mathematics emerged. And still, Leonardo Fibonacci remained obscure. Mathematicians knew about him, but the general public had never heard his name. The turning point came in the 19th century. Edouard Lucas, studying number theory, became fascinated by the rabbit problem. He explored the sequence's properties, discovered new patterns, and wrote extensively about it. He needed a name for this sequence, and he chose Fibonacci, the nickname Leonardo had used. Lucas published his work in 1877. Within a few years, mathematicians across Europe were studying Fibonacci numbers. The term entered textbooks. Students learned about the sequence, and for the first time in 600 years, Leonardo of Pisa became famous. But famous for the wrong thing. Or at least, not for the thing he'd spent his life on. The irony is thick. He wrote hundreds of pages of advanced mathematics, problems about square roots, cubic equations, geometric proofs. He taught an entire continent how to calculate efficiently. And what got him remembered? 8 numbers in a sequence that describes hypothetical rabbit breeding. This says something about how fame works. It's not about your life's work or your greatest achievement. It's about what catches people's attention. The Fibonacci sequence is memorable. It's simple enough to understand, complex enough to be interesting, and it shows up in nature, which makes it feel magical. The real mathematics in the Liber Abachi is dense and difficult. Most people don't want to work through medieval currency conversions or geometric proofs. They want something they can grasp immediately. So the rabbit problem became the hook, the way people entered Leonardo's world. Once you know about Fibonacci numbers, you might get curious about the man who discovered them. You might learn that he didn't just write a puzzle about rabbits. You might discover that he changed European mathematics forever. The sequence is the door. The rest of his work is the room you enter. But many people never walk through that door. They learn about the sequence, marvel at sunflower spirals, and move on. Leonardo remains the Fibonacci guy, not the mathematician who introduced Hindu-Arabic numerals to Europe. The substance of his achievement is forgotten, while the entertaining footnote persists. Does this matter? Should we care that people remember Leonardo for the wrong reasons? Maybe not. Fame of any kind is rare. Most people vanish completely. Leonardo could have disappeared like countless other medieval mathematicians whose names survive only in specialized histories. Instead, he's known. Students learn his name. His sequence appears in countless books, videos, documentaries. Whether they understand his full contribution or not, they know he existed. And occasionally, someone does walk through that door. They start with the sequence, get curious and discover the Liber Abachi. They learn about Hindu-Arabic numerals and the transformation of European mathematics. They realize that this man wasn't just a curiosity. He was a pivotal figure in intellectual history. Those people, the ones who dig deeper, come away with a fuller picture. The rest of us get the sequence, which isn't nothing. Fibonacci numbers have genuine mathematical importance beyond their role as trivia. They appear in algorithms, computer science, and financial markets. The golden ratio derived from the sequence influences art and architecture. The spiral patterns connect to fundamental principles in geometry and physics. Understanding Fibonacci numbers helps you understand mathematics itself. So even if people only know Leonardo for the rabbit problem, they're still learning something valuable. They're encountering a piece of mathematical beauty that happens to have a person's name attached. That person spent his life doing other things, sure, but he's the one who introduced this particular problem to Western mathematics. The credit isn't entirely misplaced, it's just incomplete. What would Leonardo think about all this? We can only guess. He might be frustrated that his serious work is overlooked. He might be pleased that any of his mathematics survived 600 years. He might be baffled that anyone cares about a simple sequence problem when there are profound geometric theorems elsewhere in his book. Or he might understand better than anyone. He was a calculator, a practical mathematician. He knew that simple problems often matter more than complex ones, because more people can use them. The rabbit problem is accessible. Anyone can understand it. And once you understand it, you've learned something about how sequences work, about how mathematical patterns emerge from simple rules. That's valuable, even if you never study advanced mathematics. Leonardo spent his career making mathematics accessible, teaching merchants how to calculate, explaining complex ideas in clear language. The Fibonacci sequence, in a way, is the ultimate expression of that goal. A mathematical pattern so simple that anyone can grasp it, so rich that mathematicians still study it, so universal that nature itself seems to follow it. If fame had to come from something, better this than nothing. But let's return to the actual work Leonardo did. Not the sequence, but the mission. He wanted to change how Europe calculated. He succeeded, but it took longer than he lived. The Liber Abachi appeared in 1202. Hindu-Arabic numerals became standard across Europe by the late 15th century. That's nearly 300 years of gradual adoption. 3 centuries during which Leonardo's work, slowly, quietly, transformed commerce and mathematics. Why so slow? Because changing systems is hard. Roman numerals weren't just numbers. They were embedded in culture, law, tradition. Merchants who'd spent decades mastering them weren't eager to start over. Scribes who'd built careers around Roman numeral accounting resisted the new methods. Universities moved slowly, as universities do. The Catholic Church, suspicious of anything from the Islamic world, didn't help. But economics won. Merchants who used Hindu-Arabic numerals calculated faster, made fewer errors, and operated more efficiently. Their businesses thrived. Others noticed and adopted the methods. Competition drove adoption more effectively than any book or decree. By the time printing presses arrived in the 15th century, making books widely available, Hindu-Arabic numerals were already dominant. The printing press just accelerated what Leonardo had started 3 centuries earlier. This is how real change happens. Not through sudden revolution, but through slow, steady pressure. One merchant at a time. One calculation at a time. One generation teaching the next. Leonardo planted seeds that took centuries to mature. He didn't live to see the harvest, but the harvest came. And now, 800 years later, we can't imagine mathematics without these numbers. Try doing multiplication with Roman numerals. Try calculating compound interest or solving algebraic equations. It's possible technically, but it's miserable. The system Leonardo championed made everything easier. Not just a little easier, dramatically, transformatively easier. That's his real legacy, not a sequence but a system, not a puzzle, but a revolution. The fact that most people don't know this doesn't diminish it. The numbers themselves are the monument. Every time you write a date, check a price, or solve a math problem, you're using Leonardo's gift to Europe. The system he learned, adopted, explained, and promoted. But Leonardo's influence wasn't confined to numbers. He did something else that changed mathematics forever, though it took even longer for anyone to notice. He introduced algebra to Western Europe. Not the word algebra, that came from Arabic mathematics, but the practice of solving problems using abstract reasoning rather than just arithmetic. Before Leonardo, European mathematics was almost entirely concrete. You counted things, measured things, calculated with specific numbers for specific purposes. The idea of using letters to represent unknown quantities, of manipulating symbols to find solutions, this was foreign. Leonardo encountered algebraic methods during his travels. Islamic mathematicians had developed sophisticated techniques for solving equations. They could find unknown values, work with abstractions, and solve problems that seemed impossible using only arithmetic. Leonardo recognized the power of these methods immediately. Throughout the Liber Abachi, he includes problems that require algebraic thinking. He doesn't use modern notation. That wouldn't develop until centuries later. But the logic is there. Finding unknown quantities, setting up equations, working systematically toward solutions. One example involves the problem of false position. You're given a relationship between quantities, but don't know the actual values. You guess, see how far off you are, then adjust systematically until you reach the correct answer. It's algebraic reasoning without algebraic symbols. Leonardo presented dozens of such problems. Each one taught merchants and scholars that mathematics could be more than just counting and measuring. It could solve puzzles, find hidden relationships, answer questions that seemed unanswerable. This was radical. Mathematics before Leonardo was a tool for practical tasks. Addition, subtraction, multiplication, division. These were for commerce and construction. The idea that mathematics could be abstract, that you could reason about unknown quantities and discover their values through logical manipulation, this opened entirely new possibilities. But here's what's strange. Leonardo never developed a systematic algebraic notation. He wrote everything in words. Long, complicated sentences describing relationships and operations. It works, but it's cumbersome. Reading Leonardo's algebraic problems feels like reading legal documents, every step spelled out in full sentences. Why didn't he create symbols, abbreviations, a more efficient system? Perhaps because he was writing for merchants, not mathematicians. Merchants dealt with practical problems expressed in everyday language. Abstract symbols might have seemed too theoretical, too removed from real-world application. Leonardo wanted people to use these methods, not admire them from a distance. Or perhaps the time simply wasn't right. Mathematical notation evolves slowly. The plus and minus signs we use today didn't become standard until the 15th century. The equals sign appeared in 1557. Algebraic notation, as we know it, using letters for variables, writing equations symbolically, didn't fully develop until the 16th and 17th centuries with mathematicians like François Viète and René Descartes. Leonardo was working 3 centuries too early. He had the ideas but not yet the language to express them efficiently. So he did what he could with the tools available. He wrote in words, explained in detail, and hoped readers would grasp the underlying logic. Many did. The Liber Abachi influenced mathematicians across Europe. Not immediately, books moved slowly in an age before printing, but steadily. Copies circulated, Students studied them. Teachers incorporated Leonardo's methods into their instruction. By the 14th century, Italian mathematicians were building on Leonardo's foundation. They called themselves the abacus masters, teaching commercial arithmetic based on Leonardo's book. These masters trained generations of merchants, spreading Hindu-Arabic numerals and algebraic thinking throughout Italian city-states. The abacus tradition became crucial to Europe's commercial revolution. As trade expanded, as banking developed, as businesses grew more complex, the mathematical tools Leonardo had introduced became essential. Double-entry bookkeeping, which revolutionized accounting, emerged from this tradition. So did sophisticated methods for calculating interest, currency exchange, and profit margins. None of this happens without Leonardo. He didn't invent these specific techniques, but he created the mathematical foundation that made them possible. Still, his name faded. By the 16th century, few mathematicians knew who Leonardo Pisano was. His work had been absorbed, built upon, and superseded. The methods he introduced had become so standard that no one remembered their origin. This is the fate of foundational figures. Their contributions become so fundamental that they become invisible. We don't think about who first taught Europe to use zero. We just use zero. We don't wonder who introduced algebraic thinking to the West. We just solve equations. Leonardo's disappearance from history makes sense in this context. His work succeeded so completely that it erased the need to remember him. The system he championed replaced the old system so thoroughly that eventually no one could imagine mathematics any other way. But there's another reason Leonardo faded. He wrote in Latin, the language of scholars. As vernacular languages became more important in the 15th and 16th centuries, as books began appearing in Italian, French, German, and English, Leonardo's work became harder to access. Fewer people read Latin. Fewer still read 13th century Latin. His books remained in libraries, but they weren't being studied. Meanwhile, new mathematicians were publishing new works in contemporary languages using modern notation. Why struggle through Leonardo's verbose Latin when you could read Luca Pacioli's clear Italian or Christoph Rudolph's German? The content might be similar, but the presentation was vastly improved. Leonardo's books became historical curiosities, important once, but now outdated, superseded by better, more accessible texts. This continued for centuries, through the Renaissance, through the Scientific Revolution, through the Enlightenment. Leonardo Pisano was a footnote, if mentioned at all. Historians of mathematics knew about him. They acknowledged his role in introducing Hindu-Arabic numerals to Europe, but he wasn't considered particularly important. Just one figure among many in the long development of Western mathematics. Then, in the 19th century, something shifted. Mathematicians started looking more carefully at the history of their discipline. Not just the great theorems and famous names, but the actual development of mathematical practice. How did people calculate in different eras? What tools did they use? How did methods spread? This new historical awareness brought Leonardo back into focus. Scholars recognized that the transition from Roman to Hindu-Arabic numerals was more important than previously understood. It wasn't just a notational change, it fundamentally altered what mathematics could do. And Leonardo had been the crucial figure in that transition, at least for Europe. Publications about Leonardo began appearing. Editions of the Liber Abachi were produced for modern readers. Historians traced his influence through the abacus tradition and into Renaissance mathematics. Leonardo's reputation was being rebuilt, but it was the rabbit problem that made him famous beyond mathematical circles. That simple sequence that appears almost as an afterthought in his book. Once mathematicians started noticing the Fibonacci sequence in nature and art. Once it became a popular topic in books and classrooms, Leonardo's name became attached to it permanently. This creates an ironic situation. Leonardo is now most famous for for something he barely cared about. The work he considered most important, introducing Hindu-Arabic numerals and algebraic methods to Europe, is acknowledged by historians but largely unknown to the public. The rabbit problem, which was just a teaching exercise, has become his legacy. Is this unfair? In a sense, yes. Leonardo deserves recognition for his actual achievements, not for a sequence that bears his name only through historical accident. But perhaps there's justice in it too. The Fibonacci sequence embodies something essential about Leonardo's approach to mathematics. It's simple but profound, accessible but rich. It starts with a practical problem, how rabbits breed, and reveals something universal about pattern and growth. That's exactly what Leonardo did with Hindu-Arabic numerals. He took a practical system used by merchants and showed Europeans that it revealed something universal about calculation and number. He made the complex simple, the foreign familiar, the theoretical practical. The sequence is Leonardo in miniature, a small thing that contains infinite complexity, a simple pattern that appears everywhere once you know to look for it. Maybe that's the right legacy after all. Still, we should remember the larger picture. Leonardo Pisano was a commercial mathematician who travelled the Mediterranean, learned from multiple cultures, and synthesized their knowledge into something new. He wrote a book that changed how Europe calculated. He introduced methods that made modern commerce possible. He planted seeds that took centuries to grow, but eventually transformed Western mathematics. And he did all this in the early 13th century, when Europe was still emerging from the intellectual isolation of the early Middle Ages. When most learning happened in monasteries and universities, focused primarily on theology and classical texts. When innovation was suspect and foreign ideas were viewed with suspicion, Leonardo looked beyond Europe's borders. He saw that other civilizations had developed better mathematical tools. He learned those tools, mastered them, and brought them home. Then he spent years writing detailed explanations so others could learn them too. This required vision, not just mathematical skill, but the imagination to see that things could be different, that the system everyone used wasn't the only possible system, that better methods existed and were worth adopting even if they came from unfamiliar places. It also required courage. Publishing a book advocating for Arabic numerals in Christian Europe wasn't safe. The Crusades were ongoing. Anything associated with the Islam was viewed with suspicion. Leonardo could have faced accusations of heresy or cultural treason. He published anyway. He argued his case carefully, pragmatically. He showed through hundreds of examples that these methods worked better than traditional ones. He made the case so thoroughly that eventually even skeptics had to acknowledge the advantages. This is quiet heroism, not the dramatic kind celebrated in stories, but the patient, persistent kind that actually changes the world. Writing clearly, teaching carefully, demonstrating patiently, trusting that good ideas will eventually win if presented well enough. Leonardo trusted in mathematics itself. He believed that showing people better methods would be enough. That practical advantage would overcome cultural resistance. That calculation was universal, transcending religious and political divisions. He was right, but it took time. 300 years, 10 generations, centuries during which his book circulated slowly, influencing mathematicians who influenced others, creating a cascade of change that eventually became irreversible. This is how transformation happens, not overnight, but through accumulated small shifts. One person learns a better method. They teach others. Those others teach more. The practice spreads through networks of students and colleagues across cities and countries through generations. Leonardo started this process. He wasn't the only factor. Economic pressure, technological development, and cultural exchange all played roles. But he was the catalyst, the person who said clearly, publicly, definitively, "There's a better way to calculate, and here it is." 800 years later, his better way is simply the way. The numbers he championed are the numbers we use. The methods he explained are the methods we teach. The vision he had of accessible, practical mathematics has been realized beyond anything he could have imagined. Every child learning to count uses Leonardo's legacy. Every scientist calculating equations uses tools he helped introduce. Every computer performing billions of operations per second uses a number system he promoted when computers were still centuries away from existing. This is impact, not fame, but genuine historical consequence. Not name recognition, but actual change in how humanity operates. And perhaps that's enough. Perhaps it's better than fame. Names fade, books are forgotten, but systems endure. Methods persist. The tools we use shape us more than the people who gave us those tools. Leonardo gave us numbers. He gave us calculation. He gave us a language for expressing quantity that works so well, we can't imagine alternatives. That gift keeps giving. Every generation benefits. Every person who counts, measures, or calculates stands on the foundation he helped build. The transformation Leonardo began didn't stop with numbers. It cascaded outward, touching everything those numbers touched. Commerce, engineering, astronomy, navigation. Every field that required calculation benefited from the shift he initiated. Consider what medieval merchants faced before positional notation became standard. Recording transactions meant writing everything out in words or using clumsy Roman symbols. Calculating profits required physical counters moved on tables. Checking someone else's work meant redoing the entire process because there was no efficient way to verify calculations. The Arabic system changed this completely. Suddenly, calculations could be written down, checked, and understood by anyone who knew the system. Business became transparent in a way it had never been before. Trust could be verified through mathematics rather than reputation alone. This had profound consequences. Trade networks expanded because merchants could track more complex transactions. Banking developed because loans and interest could be calculated precisely. Insurance became possible because risk could be quantified. The entire structure of modern economics rests on the ability to calculate reliably. And that ability came from the number system Leonardo championed. The same pattern repeated across disciplines. Astronomers could make more precise predictions. Navigators could calculate positions more accurately. Engineers could design more ambitious structures. Science itself became possible in its modern form because experiments could be quantified and results could be compared numerically. None of this was immediate. Leonardo published the Liber Abachi in 1202. The full adoption of Arabic numerals took until the 1500s. That's 13 generations. But once the transformation was complete, it was irreversible. By the time printing presses made books common, Arabic numerals were the standard. Every printed arithmetic book used them. Every merchant manual taught them. Every school primer started with them. The old Roman system survived only in ceremonial contexts. Clock faces, building inscriptions, movie credits, places where tradition mattered more than function. Leonardo probably didn't foresee all of this. He couldn't have predicted printing presses or modern science or computers, but he understood something essential, that the tools we use for thinking matter, that better tools enable better thoughts, that changing how we represent ideas changes what ideas become possible. This insight remains true today. The notation we use shapes what problems we can solve. Programming languages determine what programs we can write. Mathematical symbols determine what concepts we can manipulate. The medium constrains and enables the message. Leonardo's contribution was recognizing this and acting on it. He saw that Roman numerals constrained mathematical thinking. He knew alternatives existed. He brought those alternatives home and presented them clearly enough that others could adopt them. This required more than mathematical knowledge. It required cultural translation. Leonardo had to explain unfamiliar concepts to a skeptical audience. He had to anticipate objections and address them. He had to make the strange familiar and the foreign accessible. The Liber Abachi succeeds because Leonardo understood his readers. He didn't just present abstract theory, he showed practical applications. He worked through examples that medieval merchants actually faced. He demonstrated that these methods solved real problems that his readers encountered daily. This is the mark of an effective teacher. Not just knowing the subject, but understanding the audience. Not just explaining what you know, but translating it into terms that others can grasp and use. Leonardo spent the rest of his long life teaching. After the Liber Abachi, he wrote more books on geometry, on advanced arithmetic, on problems submitted to him by other mathematicians. He became a court mathematician in Pisa, solving problems for the Emperor Frederick II. He gained recognition in his lifetime, which is rare for mathematicians before the modern era. But the recognition wasn't for discovering new mathematics. It was for communicating existing mathematics effectively, for being the bridge between cultures, the translator of ideas, the teacher who made difficult concepts accessible. This is a different kind of genius than pure discovery. It's the genius of synthesis, of connection, of communication. The ability to see what exists in one context and recognize its value in another. The skill to take something foreign and make it native. The world needs both kinds of genius, discoverers who push into unknown territory, and translators who bring back what was found and make it usable for everyone else. Leonardo was the second kind, and history demonstrates that his contribution was just as vital. Without someone to bring back the knowledge, discoveries remain isolated. Ideas stay trapped in the cultures that develop them. Progress happens in parallel tracks that never connect. Leonardo connected the tracks. He brought Islamic mathematics to Christian Europe and showed that knowledge transcends the boundaries we draw between cultures. This message matters beyond mathematics. It's a reminder that good ideas can come from anywhere, that the familiar isn't always superior to the foreign, that progress often comes from looking outside our own traditions and being willing to learn. Medieval Europe was not naturally inclined toward this view. The Crusades were happening. Religious and cultural tensions were high. The default was to view Islamic civilization as enemy territory, not as a source of knowledge. Leonardo looked past these divisions. He saw that mathematics was universal. That calculation didn't care about the calculator's religion or nationality. This required intellectual courage. Not the dramatic kind, but the quiet courage to think independently, to form judgments based on evidence rather than prejudice, to advocate for truth even when truth came from uncomfortable sources. The courage paid off. Not immediately for Leonardo himself. He died in relative obscurity, his later years poorly documented, but for civilization. The knowledge he transmitted became foundational. The system he promoted became universal. The vision he had of mathematics as a practical, accessible tool was realized. Today we take this for granted. Numbers seem natural, obvious, the only possible way to represent quantity. But they're not natural. They're invented. They're a technology, refined over centuries, improved by many cultures, and transmitted across vast distances by people willing to learn from those different from themselves. Leonardo was one link in a long chain. The Babylonians invented positional notation. The Indians added the zero. The Arabs refined and transmitted the system. Leonardo brought it to Europe. Countless teachers after him spread it further. Each link mattered. Remove anyone, and the chain breaks. But some links are more crucial than others. Leonardo's link connected two worlds that might otherwise have remained separate. He was positioned uniquely in space and time, born in a trading city, raised in a merchant family, educated in North Africa, living in an era when Europe was beginning to develop the commercial infrastructure that would need better calculation methods. He could have ignored what he learned. He could have used Arabic numerals privately, for his own advantage, and kept the knowledge to himself. He could have decided that translating Islamic mathematics for Christian readers was too controversial or too difficult. He did none of these things. He wrote the book, he shared the knowledge, he started the transformation. And here we are, 8 centuries later, still using what he taught, still counting with his numbers, still calculating with his methods, still benefiting from his decision to be a bridge between worlds. The classroom where children learn arithmetic today would be unrecognizable to Leonardo in many ways, but the numbers on the board would be familiar. The methods being taught would be ones he knew. The basic framework he worked within remains our framework. This is the deepest kind of legacy, not monuments or wealth or fame, but change in how humans operate at the most basic level. Not your name remembered, but your contribution embedded so deeply in everyday life that it becomes invisible. Leonardo gave us something we use so constantly that we forget it's there. Numbers aren't nature, they're culture, they're a choice. They're a tool that someone had to introduce, and someone had to adopt, and someone had to spread. He was the someone who started that process in Europe. The catalyst, the translator, the teacher, the patient explainer, who believed that showing people better methods would be enough. He was right. The methods won. Not quickly, but inevitably. Not through force, but through demonstrated superiority. Not by replacing human judgment, but by augmenting it. This is how good ideas spread. Not through conquest, but through convincing. Not by destroying what came before, but by offering something better. Not overnight, but through accumulated decisions by individuals who recognize value when they see it. Leonardo trusted this process. He trusted that calculation was universal enough and useful enough that people would adopt better methods once they understood them. He trusted in mathematics itself as a force that transcends cultural boundaries. History proved him right. The numbers spread. The methods stuck. The transformation completed. And now we live in the world he helped create, where calculation is accessible to everyone, and numbers are the language we use to describe reality itself. Every equation written, every measurement taken, every transaction recorded, every scientific experiment quantified. All of this happens in the notation Leonardo promoted. All of this rests on the foundation he helped lay. That foundation is now so solid we can build anything on it. Skyscrapers and satellites, computers and quantum physics, financial systems and space programs. None of it would be possible without the ability to calculate reliably. And that ability came from the number system Leonardo fought to introduce. He didn't invent the system. He didn't discover anything new, but he did something just as important. He recognized what was valuable, learned it thoroughly, brought it home, and explained it so clearly that others could learn it too. This is a replicable model. Find what works elsewhere, learn it deeply, translate it carefully, share it generously. Trust that good ideas will spread if presented well enough. Be patient because transformation takes time. Be persistent because resistance is inevitable. Be confident that practical advantage eventually overcomes cultural inertia. Leonardo did all of this. He was the right person in the right place at the right time with the right combination of skills and circumstances. He saw the opportunity and seized it. He did the work that needed doing. 8 centuries later, every person who counts uses what he taught. His legacy isn't his name. Most people don't know it. His legacy is the system itself, woven so thoroughly into human civilization that we can't imagine alternatives. That's the kind of contribution that matters most. Not fame, but function. Not recognition, but reality. Not being remembered, but being used. Leonardo gave us tools that work so well, we've forgotten their tools. We think they're just how numbers are, but they're not. They're how numbers became, and Leonardo helped make them that way. The classroom is quiet. A teacher writes numbers on a board. 1, 2, 3, 4, 5. The students copy them down, barely thinking about what they're doing. These symbols are so familiar, they seem inevitable, like they've always existed, like they're part of nature itself. They're not. Someone had to bring them here. Someone had to see them in a foreign land, recognize their value, learn them thoroughly, and carry them across a sea to a place that had never seen them before. Someone had to write a book explaining what these strange symbols meant and why they mattered. Someone had to spend years demonstrating that, yes, this unfamiliar system really was better than what everyone had always used. That someone was a merchant's son from Pisa who travelled to North Africa as a boy and came home with knowledge that would reshape a civilization. He wrote his book in 1202. Most copies of it were lost. His name was forgotten for 600 years. He died in obscurity, probably in the 1240s, with no record of when or where or how. But every calculation you've ever performed uses what he taught. Every price you've checked, every measurement you've taken, every equation you've solved. The numbers are his legacy, though he didn't invent them. The system is his gift, though he didn't create it. What he did was harder than invention. He saw something valuable in another culture and brought it home. He translated it, explained it, demonstrated it, trusted it. He believed that practical advantage would overcome centuries of habit. He was right, but it took 10 generations to prove it. Think about what that means. The man who changed how Europe calculated never saw the full result of his work. He died before Arabic numerals became standard. He never witnessed the scientific revolution those numerals would enable. He never imagined computers processing billions of calculations per second using the base 10 system he promoted. He planted seeds knowing he'd never see the harvest. He did the work anyway. This is the pattern of real change. Not dramatic revolutions that transform everything overnight, but patient accumulation of small shifts. One merchant adopts a better method. Another follows. Teachers incorporate it into their lessons. Students learn it and teach their own students. The practice spreads through networks of exchange, across borders, through generations. 3 centuries after Leonardo published his book, Roman numerals were effectively dead, killed not by decree or force, but by obsolescence. The old system couldn't compete with the new one. Math itself chose the winner. And here's what's strange about Leonardo's fame, or lack of it. The work he cared most about, introducing Hindu-Arabic numerals to Europe, teaching algebraic methods, solving complex problems, is acknowledged by historians, but unknown to most people. What made him famous was a throwaway problem about breeding rabbits, a sequence he barely emphasized, presented as a curiosity, buried in hundreds of pages of serious mathematics. That sequence bears his name now. Most people who recognize Fibonacci couldn't tell you anything else he accomplished. This seems unfair until you realize that the sequence embodies everything Leonardo represented. It starts simple, 1, 1, 2, 3, 5, and reveals infinite complexity. It appears in sunflowers and galaxies, in art and architecture, in places Leonardo never looked and couldn't have imagined. It's accessible enough for children to understand and profound enough that mathematicians still study it. It's practical and theoretical, familiar and mysterious, ancient and modern, all at once. The sequence is Leonardo in miniature, a small thing that contains everything, a pattern that spreads everywhere once you know to look for it. Just like the number system he championed, which started in one culture, travelled through others, and eventually became universal. Just like the mathematical methods he taught, which seemed foreign at first but proved so useful they became standard. Just like the vision he had of calculation as something accessible to everyone, not just specialists with abacuses. That vision is reality now. Walk into any school anywhere in the world and you'll find children learning to add, subtract, multiply, divide, using Hindu-Arabic numerals. Using methods that trace back to the Liber Abachi and the abacus tradition it spawned and the centuries of accumulated practice that followed. Leonardo's contribution is so thoroughly absorbed into daily life that it's invisible. We don't think about who taught Europe to calculate. We just calculate. This is the highest form of success, not being remembered, but being used. Not fame, but function. Not your name on monuments, but your work embedded so deeply in civilization that it becomes foundational. The numbers Leonardo taught are now simply how we count. The system he championed is now simply how mathematics works. The transformation he started is now complete and irreversible, and yet he remains somehow unknowable. We don't know what he looked like. We don't know his exact birth date or death date. We don't know his personality beyond what can be inferred from his writing. We don't know if he had a family, what he believed about religion, what he thought about politics, what he did in his final years. The documentary record is thin. The man behind the mathematics is shadowy. Perhaps that's appropriate. Perhaps it's better this way. Names and faces fade. Personalities become distorted through historical distance. But the work remains. The ideas persist. The methods continue functioning regardless of who first taught them. Mathematics transcends biography. Truth doesn't care about the truth finder's life story. What matters is that someone did the work. Someone saw that better tools existed. Someone learned them thoroughly. Someone brought them home and explained them patiently and trusted that practical advantage would eventually win. Someone started the transformation that would take centuries to complete, but would ultimately succeed. Leonardo was that someone. Not because he was uniquely brilliant, though he was clearly talented, but because he was positioned correctly and made the right choices. He could have kept his knowledge private. He could have decided that translating Islamic mathematics for Christian Europe was too controversial. He could have written exclusively for specialists rather than trying to reach merchants. He made different choices. He wrote the book that needed writing. He did the work that needed doing. 800 years is a long time. Empires have risen and fallen. Technologies have appeared and become obsolete. Languages have evolved beyond recognition. But the numbers Leonardo taught are still the numbers we use. The sequence that bears his name still appears in nature and art. The foundation he helped build still supports everything we calculate. That foundation is invisible now. We stand on it without noticing it's there. We use tools without thinking about their origins. We count without wondering how we learned to count. This is the fate of foundational contributions. They become so basic that they disappear from consciousness. We forget that someone had to introduce them. We forget that things could have been different. We forget that the familiar was once foreign and the obvious was once revolutionary. But occasionally, it's worth remembering, worth acknowledging that the tools we take for granted had to be created, refined, transmitted, taught. Worth recognizing that knowledge doesn't appear spontaneously, but travels through human networks across centuries and continents. Worth appreciating that someone, somewhere, did the patient, unglamorous work of translation and explanation that makes our comfortable assumptions possible. Leonardo did that work. He translated not just symbols, but entire ways of thinking. He explained not just how to calculate, but why calculation mattered. He demonstrated not just that Arabic numerals were different, but that they were better. He trusted not just in mathematics, but in people's ability to recognize value when shown it clearly enough. History proved him right. The numbers spread. The methods stuck. The transformation completed. And now we inherit the result without necessarily understanding the process. We use what he taught without knowing his name. We benefit from his work without acknowledging his contribution. This isn't tragic. It's how progress works. The people who build foundations rarely get credit for the structures built upon them. The teachers who make knowledge accessible are overshadowed by the students who advance that knowledge further. The The translators who bridge cultures are forgotten once the bridge becomes a highway. Leonardo would probably accept this. He was a practical man, writing for practical purposes. He wanted people to calculate better, not to remember him. He wanted methods to spread, not fame to accumulate. He wanted mathematics to be accessible, not credit to be assigned. The fact that his system succeeded so completely that it erased his name from popular memory is, in a strange way, proof of his success. The work mattered more than the worker. The contribution mattered more than the contributor. The transformation mattered more than the transformer. This is the highest form of historical impact. Not being celebrated, but being used. Not being remembered, but being foundational. Not your name surviving, but your work becoming so essential that it seems to have always existed. Leonardo gave us numbers. He gave us calculation. He gave us a system that works so well we can't imagine alternatives. He gave us tools that enabled everything that came after: the scientific revolution, the industrial revolution, the information age. None of this was possible without the ability to calculate reliably and efficiently. That ability came from the number system he promoted. That system came from the book he wrote. That book came from the travels he undertook, and the knowledge he gathered, and the explanations he crafted. Every number you write connects back to Leonardo. Every calculation you perform uses methods he introduced. Every equation you solve rests on foundations he helped build. The connection is invisible, but unbreakable. He changed how we count, and counting underlies everything we do. The teacher writes numbers on the board. The students copy them down. Nobody thinks about Pisa or North Africa or the year 1202. Nobody thinks about the centuries of gradual adoption or the resistance that had to be overcome, or the cultural translation that had to happen. Nobody thinks about Leonardo at all, but the numbers are there. The system works. The foundation holds, and somewhere in the long chain of transmission that brought these symbols from ancient India, through the Islamic world, to medieval Europe, and finally to this classroom, to these students, to this moment, Leonardo Pisano stands as one crucial link. Not the first, not the last, but essential nonetheless. He did his part. He passed the knowledge forward. He trusted that others would receive it and use it and pass it forward again. He was right to trust. The knowledge kept moving. The methods kept spreading. The transformation kept accelerating until it became complete and irreversible. That's the worker. That's the contribution. That's the legacy. Not monuments or fame or even recognition. Just the quiet satisfaction of knowing that you made the world slightly better by sharing something valuable that you learned. Just the knowledge that future generations will benefit from what you taught, even if they never know your name. Just the confidence that good ideas spread if explained well enough and given enough time. Leonardo had that confidence. He wrote his book and let it speak for itself. He solved his problems and moved on to the next ones. He lived his life and left his work behind. The work survived. The work mattered. The work continues mattering 8 centuries later. And that, in the end, is enough. More than enough. Everything that matters. The numbers remain. The sequence continues. The foundation holds. This is how we count now. This is how we calculate. This is how we measure and quantify and make sense of the mathematical structure underlying reality itself. Leonardo helped give us this. That gift keeps giving. That gift will keep giving for as long as humans calculate. The work is done. The transformation is complete. The revolution that took 300 years to finish is finished. And somewhere in the foundation of it all, invisible and essential and permanent, is the contribution of a man who never existed, at least not by the name we call him, but who changed mathematics forever. Fibonacci, Leonardo Pisano, the calculator from Pisa, the traveller who brought back numbers, the teacher who explained patiently, the bridge between worlds, the translator of knowledge, the patient revolutionary who trusted in the slow accumulation of small changes. His numbers are everywhere now. Look around and you'll see them. On price tags and calendars, in textbooks and bank statements, measuring time and distance and quantity, describing the world in the language he helped make universal, the language of calculation, the language of numbers, the language that transcends borders and cultures and centuries. This is what one person can do, not through brilliance alone, not through fame or power, but through patient work, through learning what's valuable, through bringing it home, through explaining it clearly, through trusting that others will recognize its worth, through doing the unglamorous, essential work of translation and transmission and teaching. The world changes one calculation at a time, one person learning, one person teaching, one method spreading, one generation passing knowledge to the next. Leonardo understood this. He did his part. The chain continued without him. The work he started finished without him. The transformation he initiated completed without him knowing it had succeeded. But it did succeed, completely and permanently and irreversibly. The old system is dead. The new system reigns, and every number we write, every calculation we perform, every equation we solve stands as testament to the man who brought these tools to Europe 800 years ago and trusted that they would spread. They spread, they conquered, they became universal, and Leonardo, forgotten and rediscovered, and famous for the wrong reasons, and essential nonetheless, remains the hinge between what was and what is.